Hello and welcome to the MOOC on optical communications. We will be talking about fiber nonlinear effects in this module. So far when we have discussed fiber, we have looked at the propagation constant of a fiber, we have derived the modes of a fiber, we have seen what kind of effects does this fiber have on a pulse that is propagating, right. So, we have seen that the amplitude of the pulse might reduce because of the loss in the fiber, right, which happens because of various reasons that we have already told you in the earlier modules, and the pulse would spread out in time because of the chromatic dispersion. So far what we have seen is only loss and dispersion, and there is also one other thing which I would like to tell. Now when these pulses carry information, right, occasionally because after this one you put a photodetector, right, and then you look at what is the received signal and then demodulate the received photocurrent, you will get the information back. You will get the information back which, let us say, you have transmitted as 1, 0 and so on. If you start increasing the launch power, that is the power P in that you have used in order to transmit through not just one fiber, you might have transmitted through multiple fiber followed by an amplifier, fiber followed by an amplifier and so on. This was called as the long haul communication, right. So, in this long haul communication system, one of the expectations that you would have had is that if I am increasing the launch power P in, the power that I am using at the transmitter, if I start increasing this power, then the BER of the system should go down. This is what normally one assumes, which is very true for a wireless communication channel or a copper cable channel, that as the power increases, because the signal to noise ratio is increasing, the bit error rate should drop, because the bit error rate is directly proportional to how much signal to noise ratio that you have. Unfortunately, what you would find in an optical communication system is that as you start increasing the launch power, the BER decreases. So far there is no surprise, but after reaching a certain optimum power, the BER again starts to rise. Okay. This power is what we call as the optimum launch power, and that represents the maximum launch power that a particular system that you have used will be able to sustain. This portion there is no surprise. The reason why BER decreases is when your input power increases, the photocurrent that you would get would also increase, and hence your BER would drop. But what accounts for the increase of BER in this region? What accounts for the increase of BER in this region is not something that you would know if you have just studied the radio channels, but this one happens because of the nonlinear effects in the fiber. Okay. As the launch power increases, the power density, so if you look at the power density is given by how much power that you have sent in to the area of the fiber. Okay. So, this, or rather you can call this as the intensity itself. So, rather than calling this as power density, you can call this as the intensity itself, and you see that this intensity keeps on increasing as P in starts to increase while you keep the area constant. Okay. Of course, the other way would be that if you keep the same P in but change the fiber area, that would also increase, but that is not what you normally do, right. So, as the power increases, the area remains fixed, but the intensity increases. And optical systems have this peculiar thing that if the intensity increases beyond a certain value, then the linear relationship between the vectors D and E simply breaks down. We are used to seeing the relationship of D and E vectors as D is equal to epsilon 0 times E, but when the intensity increases sufficiently, then you start seeing, in addition to this linear term, you start seeing nonlinear terms. Okay. So, you start seeing nonlinear terms beginning from this one. So, this is given by, so there are a lot of other ways of representing this, but these are the first three terms that I have written. This is the linear susceptibility term. Okay. Together with epsilon 0 of the free space, this will define the permittivity, relative permittivity, and this relative permittivity is still linear, but it could be of course anisotropic and inhomogeneous, but this will not be nonlinear. However, these effects which are the nonlinear susceptibilities, this chi 2, chi being the susceptibility term, chi of 2 represents the second order nonlinearity, chi of 3 represents the third order nonlinearity, and if the system happens to be, the intensity happens to be much higher, then one can even expect the fourth and the fifth order nonlinearities to be present. In a silica glass fiber, why would the intensity increase? Well, the launch powers are increasing, but the powers values that you are using are typically say 1 milliwatt or let us say 10 milliwatt or so. So, by power itself it is not very high, but the intensity is high because the area of a single mode fiber is very small. Remember or recall that the fiber has a core radius of about 4 micron. So, the area that you are looking at, the core radius is 4 micron. So, the area that you are looking at is pi into r square, where r is 4 micron. So, you have 4 square into 10 to the power minus 12 multiplied by pi, 4 square is 16, 16 into 3 is what one can think of, right. So, that is about 48 or so micrometer square, or 48 micrometer square would be the effective area. So, you look at what would be the intensity here. You have a 10 milliwatt power, right, in 48 into 10 to the power minus 12 meter square. Okay. So, if you see here and then pull this 10 to the power minus 12 onto the numerator and forget that this 10 and there is a 48, you can imagine, or you can approximate it as 50. So, that 0 0 cancels. So, what you have is 0.2 into 10 to the power 9. Now, this 10 to the power 9 is a real culprit because it is actually increased the intensity so much. So, increased intensity causes nonlinear effects, and these nonlinear effects are normally classified into two types. One is called as the scattering effects. Scattering phenomenon such as the Brillouin and the Raman effect. The Raman effect is the simple Raman effect that you are all familiar with in the crystalline cases, but it is also present in the optical fibers as well. Okay, so these effects we are going to talk about it later, but the scattering effects are one type of nonlinear effects. These scattering effects invariably lead to loss in the signal power. Okay, so if you have a certain power which is at lambda s, then these nonlinear effects will generate additional waves. In addition to lambda s, they would also generate additional waves which would be shifted, or which would be generated both on the lower wavelength side as well as the higher wavelength side. So, you have let us say lambda 1 and lambda 2, okay, both Brillouin and Raman, and in the process the power in lambda s actually decreases because it would have transmitted some amount of power to these wavelengths. Okay. So, as the signal propagates, remember there are these WDM channels, other signals are also propagating at other wavelengths. So, one of these wavelengths starts to interact with the fiber and starts to give out power to the other one. So, even if you have started everyone to have an equal power, but at the end of the fiber this might be the condition. Some of the channels would have had higher power, some channels would have had lower powers, right. So, the power or the signal to noise ratio in this channel will be very small compared to the signal to noise ratio in this channel. Okay. If that was the only case, that one would have tried something, you could have put a different optical amplifier to each of that. But more importantly, if the information carried is not just in the amplitude but it's also in the phase, then these wavelengths will talk to the other, or this particular channel which has given up the power not only has given up the power, it has also introduced a certain amount of crosstalk with this particular wavelength channel. So, this scattering effect leads to loss of power as well as to crosstalk. There is another group of nonlinear effects that will take place in a fiber, and these are the non-scattering effects. These are called as self-phase modulation, cross-phase modulation and 4-wave mixing. As their names suggest, self-phase modulation is any change in the phase, and self-phase modulation means that the phase of the signal as it propagates through the fiber will change because of its own power. Okay. Because there is a power and this power is fluctuating slightly, the phase, the power fluctuations also get transferred to the phase of its own signal, right. So, this is sometimes called as AM PM fluctuation, that is amplitude fluctuations getting transferred into phase fluctuations. In the cross phase modulation, the phase of this wave, which is at lambda 1, will be affected by the power in another wavelength, which is lambda 2, and of course any other powers lambda 3, lambda 4 and lambda 5 and so on. Okay. So, the power in additional channels or in the other channels affecting the phase of this channel which you are interested in is called as the cross phase modulation. Okay. The 4-wave mixing process is even more dangerous, because if you start with let us say only 3 wavelengths over here, at the output of this one you are going to see a 4th wavelength. This 4th wavelength is called as the FWM product, and this 4th wavelength, it is not just one wavelength that would happen. Now because there is fiber still continuing, these 3 will now talk to each other and generate another wavelength, which will then talk to the existing wavelengths and generate additional products. So very soon you will see that these modulation terms, the intermodulation type of terms or the FWM product terms start increasing in product. Okay. So you start with only 3, you get the 4th one. We start with 4, you are going to get additional ones, and in general if you start with n, the terms that you are going to get because of the n wavelengths that are present and interacting with each other would be about n square by 2. So these effects, nonlinear effects, will reduce the performance of the system because they will start to increase the bit error rate. Okay. How do we actually model this nonlinear effects? The question of modeling nonlinear effects is a very complicated one, which we are not going to get into, but one can find out some parameters which will capture the essence of these nonlinear effects or over the range where the nonlinear effects will happen. And one such parameter is what is called as the effective length of the fiber. The effective length of the fiber is the length over which nonlinear effects are predominant, or they are very dominant over that particular length. How do we obtain that? We know that if I start increasing the length of the fiber, right. So if I start increasing the length of the fiber, right, the power here, if you start with a power of P in, the power actually reduces exponentially, correct. The power reduces exponentially and is given by P in e power minus alpha z, where alpha is the attenuation coefficient of the fiber. Now if I consider a certain length L and then find out what is the total power that has been present in this particular length L of the fiber, so starting from z equal to 0, I can obtain the total power by looking at 0 to L and integrating this power profile, right. So if I integrate this power profile, and integral of e power minus alpha z is minus 1 by alpha, and then you put in the 2 limits here, so you can show that this would be 1 minus e power minus alpha L divided by alpha. We can consider the term that is in the bracket as the effective length L effective in such a way that the power P in times L effective is actually equal to the total power that is contained within this one. So this is divided by alpha. In this effective length, one can assume that the power is actually constant. So if you assume that the power is constant with a value of P in over the effective length that we have considered, then the area under this P in into L effective will be the same as the area under that P in over that particular length L. Okay. So actual length L might be different while the effective length will be somewhat shorter. So the actual length might actually be larger, but effective length over which the nonlinear effects are predominant would be smaller, and this is given by L effective is 1 minus e power minus alpha L by alpha, and when alpha into L is very large, e to the power minus alpha is approximately 0. So L effective is approximately 1 by alpha. For alpha of about 0.2 dB per kilometer, this corresponds to about 20 kilometers. Okay. So this corresponds to about 20 kilometer for an attenuation of 0.2 dB per kilometer at around 1550 nanometer, which means that when you have a link of 80 kilometers, the first 20 kilometer is very crucial because that is where the nonlinear terms are predominant. And nonlinear effects actually depend exclusively on the amount of power that you have. So the larger the power, the larger will be the effect of the nonlinearity. But nonlinearity starts to decrease with the length because the power starts to decrease with length. A different criteria that we normally, in addition to this effective length that we employ is what is called as the effective area. Suppose if I look at the fiber radius, okay, and as the fiber radius starts to increase, the intensity profile actually starts to decrease. The actual intensity distribution across the fiber core in the fundamental LP01 mode also starts to decrease as the length of the fiber radius increases, or as a position of the fiber radius. Okay. Effective area is defined by that value of R effective, the radius effective, and correspondingly pi into R square A effective, which is equal to the area effective, in such a way that much of the power is actually concentrated within this region. Okay. So, this is the definition of the effective area, and for a 1550 nanometer G652D fiber, which is the low water peak fiber that you can buy from market, the effective length will be about, the effective area will be about 72 micrometers. However, this effective area increases, effective area decreases to 21 micrometer square for a dispersion compensating fiber at the same wavelength 1550 nanometer. Okay. This is actually very important, because if you use a dispersion compensating fiber in order to compensate for the dispersion, then you see that the reduced A effective means that the intensity would be higher over here. For the same average input power, the intensity would be higher over here, and hence the nonlinearities will be quite high. So, you get a high nonlinearity, whereas the nonlinearity will be present, but it will not be as significant as for a DCF system. So, most of the legacy systems have actually been laid down. So, after you have a fiber, you normally put in a DCF. Okay. So, you have a DCF and then amplify, and then you have the next span, then you have the DCF, and then you have an amplifier followed by this, and so on. Okay. But people realized that these systems which have a DCF in between in order to manage the dispersion were actually contributing to a large amount of nonlinearities. Okay. So, that is one of the trade-offs that one has to perform, dispersion versus nonlinearity. The general rule is that if you have a high value of dispersion, then nonlinearity will be significantly low, but of course, you will pay price in the form of not having enough bit rate because of the high dispersion. But if the dispersion is low, the nonlinearities will be very high. This case, having nonlinearity high is not so bad, because there are some useful applications to nonlinearities as well. Okay, some of those applications we are going to see later, but there are some useful applications to nonlinearity. Okay. What we will do now is to look at in brief what about this self phase modulation, cross phase modulation, and 4-wave mixing. Okay. Self phase modulation, as we have said, is the modulation. So, we are already familiar with what phase modulation means. Phase modulation is, if you start with a signal, let us call this as E of t, okay, which is the envelope of the signal, let us say. So, this E of t, the electric field or the envelope of this one, would have a certain phase, its phase would be modulated. So, that would be e to the power j phi of t. However, if this phase depends on the input optical power, or it would depend on the intensity I of t, right, and whose I of t are we talking about? It is actually the intensity of its own wavelength, right. So, if I am looking at the self phase modulation of the signal, which is at some e to the power j omega 0 t, right. So, if the same pulse, if the intensity is basically E square, right. So, if the intensity of its own wave contributes to the phase fluctuations, then this is called as self phase modulation. One can understand this by changing the refractive index representation, right. See, we normally use the refractive index and then call this as C by V, right. It is the ratio of the light speed in air to the speed in a region that is not air in a medium, but this refractive index can be reformulated when you have nonlinearities into the linear part n0 plus the nonlinear part, which will actually be given by n2 into I, where I is the intensity and n2 is the second order nonlinearity or the nonlinear refractive index. In the fibers, we see that the chi2 term actually vanishes because of the symmetry in the fiber. So, the lowest order nonlinearity will be chi3 term, okay, and this effect chi3 into E into E into E can be modeled as n2 into I by modifying the refractive index of the fiber. So, n0 is the linear part and n2 into I is the nonlinear part of the refractive index. You might say, what have we done by modeling the refractive index? Well, look at the phase. The phase change is given by 2 pi by lambda into n, right, over a length L, let us say. So, the phase change that you are going to get would be this particular component. Now, substitute for n here. So, you get 2 pi by lambda into n0 L, which is the linear phase change that you would have seen, right, as the wave would propagate through the fiber. This is the linear phase change that you would have seen, but because of this term n2 into I, you are also going to see the nonlinear term over here. and instead of talking about N2 into I, there is an equivalent version in which you can replace the nonlinear coefficient by another coefficient gamma, which is measured in per watt kilometer, and you have a power P, and you see that the nonlinear phase change, right, or the nonlinear phase shift is given by gamma P into L. Okay. Therefore, this becomes gamma P into L, okay, where P is measured with respect to the effective area, or sorry, the effective area is taken into account in terms of the gamma parameter. Okay. So, this is the nonlinear phase shift, and when the power is not constant, when you are actually transmitting pulses, the power will not be constant and power will actually change with time. So, the nonlinear phase shift or the nonlinear term will start to change with phase. Okay. And where would this self phase modulation be important? Suppose you are transmitting, QPSK signal, or let us say you are transmitting a QPSK signal. What would the self phase modulation do? As the pulses propagate through the fiber, these points would start to move away, right. So, the points would actually start to move away in this fashion, and because this self phase modulation actually talks, or the nonlinear effects in the fiber actually talks to the amplifier noise that is present, there will also be some sort of a noise distribution around this one. So, you will actually see that there is this noise distribution as you go through. And if the self phase modulation is pretty strong because the nonlinear effects is strong, then it is possible that these constellation points move in such a way that they would enter into the other decision regions. So, remember, these were the decision regions, and because these points have moved into the other group as well, there would be considerable bit error rates. Okay. So, the larger the self phase modulation, the larger will be the bit error rate, and if you are interested, you can look at this particular paper which talks about how to overcome this nonlinear effects, or how to estimate these nonlinear effects in the presence of the amplified spontaneous emission noise as well as the laser phase noise. Okay. You have this paper which is IEEE COM letters in 2016. The paper is titled as Tracking Linear Phase Noise and Nonlinear Phase Noise in 100 G QPSK systems. Okay. So, you can look at this paper which extensively talks about how to estimate this nonlinear phase noise, and you will actually see there, if you look at the graphs in the paper, you will see that these self phase modulation that you have obtained because of the fiber nonlinear effects can cause significant bit error rate, and it has to be mitigated in order to improve the performance of the system. In WDM systems, you get an additional phase modulation, and this time the phase modulation depends on the channel which is not even which is not even the channel of your interest. Suppose your channel of interest is in the wavelength at lambda 1 having a electric field E1 of t. Okay. Now, let us say co-propagating along with this E1 of t would be another data carrying channel in the wavelength lambda 2, and let us say that this lambda 1 and lambda 2 are sufficiently closely spaced. Then there will be a nonlinear phase shift in addition to the phase shift that happens because of the presence of its own wavelength. There would also be this additional term which is twice as efficient as E1, okay, which is as efficient as the self phase modulation. So, E1 is my channel, the phase shift of this one depends on the power fluctuations of this channel itself, which is called as a self phase modulation. But if there is a parallel co-propagating channel at another wavelength which is close to this lambda 1, the power fluctuations in this channel will be transferred onto the phase fluctuations of this particular channel, which is my channel, right, and this one happens with twice the efficiency than the SPM. This additional phase shift which occurs because of the co-propagating channels is called as the cross phase modulation. Okay. This is sometimes denoted by XPM, X standing for the cross. So, cross phase modulation refers to the phase modulation because of some other channel in the system. Of course, it is not just only 2 channels. If there are 200 channels propagating, then the phase of one particular channel will be affected by 199 other channels. In addition to it, the phase will be affected by its own power, okay, when you have nonlinearity in the fiber and at very high powers that you have transmitted. So, this is called as the cross phase modulation. 4-wave mixing is another non-scattering nonlinear effect. In the 4-wave mixing phenomenon, what happens is, if you have 3 frequencies. Okay, it is rather easily discussed in terms of the frequency. So, I am going to go back to the frequency notation, not the wavelength notation here. So, if you have omega I, omega j and omega k, these 3 wavelengths or the 3 frequencies interact with each other inside a nonlinear fiber or inside a fiber, okay, which exhibits nonlinear effects, which means that the powers here we have assumed to be are also pretty high to generate what is called as the idler. This idler has the frequency of ijk, or the frequency we have defined it to be ijk. Let us call this ijk as L, and it is given by omega I plus omega j minus omega k. Okay. This new frequency is called as the FWM product, or sometimes called as the idler wave. Okay. This idler wave would involve the 3 frequencies in such a way that they will start eat up the power here, and in a worst case scenario, let us say one of these omega L happens to fall on another data carrying channel. So, let us say this is my data carrying channel whose frequency is omega L, but because of the 3 wavelengths that are present in the channel propagating alongside the data carrying channel, there will be a new product which is the FWM product generated at omega L, and this product happens to fall on the data carrying channel itself, leading to crosstalk. And this crosstalk is very, very important because it adds incoherently to the signal. Okay, it is kind of a Gaussian noise. One can model this as a Gaussian noise adding to the particular data carrying channel, and this is again very difficult to predict because there are these channels which are turning on, turning off. So, there is a statistical distribution to this crosstalk that is induced on the data carrying channel, and that becomes very important, okay, because it reduces the performance of the system. However, FWM also has its own advantages or own uses because it can be used to convert data in one wavelength to a data in the other wavelength without actually demodulating that from optical to electrical, then modulating back onto the other channel. You can use the FWM process to supply 2 additional pumps, and then you can also tune these 2 pump frequencies in such a way that you can have a tunable wavelength converter. Okay, this is one of the major uses of 4-way mixing. 4-way mixing also has additional uses in terms of optical phase conjugation. The generated idler can be made to behave in such a way that its phase will be conjugate of the signal. Then you can take the phase conjugator, which is realized by an FWM process, put it in the middle of the link. Okay. Whatever the variations that this data carrying channel has experienced in the first half of the fiber can be simply inverted, and that the variations can be removed by placing this after the phase conjugator. Okay. So, these are some of the advantages of FWM, but make no mistake, any of these nonlinear things that we have discussed, nonlinear effects that we have discussed will result in reduction in the performance of the system, and people are spending a lot of effort in overcoming these nonlinearities. In fact, one cannot completely cancel the nonlinearities, one can only mitigate these nonlinearities, and that is what people are trying to do. So, we will stop here and take up some additional things involving nonlinear effects in the next module. Thank you very much.